the last time you see of me. Yeah, I'm not going to participate. I will be actually in the audience next week most of the time, so we're going to have a chance to discuss, if you want, the things that we have. Now, this presentation, we are going to be doing it together with Manuel Blanco, Professor Blanco. He's not here yet, but I think he's in Cyprus. He'll be coming at some point. I also did it last year. It was enough for 1.5 hours, but this time we may have to run the slides a bit quicker because the last half an hour will be devoted to what Manuel is going to say. So the title that you have on the sheets there, it's different to this one. This is the title of my talk, but I think it's called something like Deterministic and Stochastic approaches. Yeah. So anyway, I will be talking about the deterministic approaches, let's say the classical approach to looking at the finance and economics of CSP plans. Manuel will be talking more about the risk assessment and what I showed you a bit yesterday morning about what the Monte Carlo we do for. Anyway, you'll see. So this is mainly the topics I'm going to be talking about. The first part of the talk is it's a bit boring, sorry to be honest. It's about the investment basic tools. We'll be talking about these indicators that somebody asked yesterday, about the NPV. We're talking about what the present value is, the NPV, the IRR, and of course the LCOE, which is the main metric for all energy and electricity plants. We'll talk about, again, for the main CSP technologies, the capacity factor, the solar multiple, and a few things about upfront costs and O&M for CSP plants. Then we'll talk briefly about WACC, the weighted average cost of capital and financing cost. This is a bit more advanced topic. We're not going into in much detail. A few examples about the future cost estimates and the argument for CSP between value and cost. Now, let's start with the basics. The time value of money. Well, you might be familiar with that or not. This talk is going to be covering, I hope, the fundamentals. So if you have any questions, please stop me. The idea that money is available at the present time is worth more than it is in the same amount in the future. And the reason is that money has interest earning potential, which means that provided that you have money and they can gain interest, any amount of money is worth more the sooner it's received. Which means basically that the amount of money you have now is worth more than the same amount of money that you have in the future. Because this amount of money you have now, you can potentially invest it and gain interest. Okay. This is, so it's here described, a euro or a dollar or whatever currency you want can be invested and earn a day's worth of interest, making the total accumulate worth more than a euro by tomorrow. Okay, this is the concept behind the time value of money. Now, the investment projects have certain initial installation or capital cost, as they call it, and have a series of financial cash flows for the future over time. The cash flows come from selling the commodity that you're producing, electricity, water, whatever it is. And also there's a negative cash flow for the operation and maintenance that you have to pay. Now, to assess the project feasibility, all these present and future cash flows must be equated to a common basis, okay? Because as we said, we have the time value of money, and whatever cost we'll be incurring in 5 years' time doesn't have the same value as it is today, for this principle that I explained earlier. So this method is called discounting. It's the method by which these various future cash flows are expressed at the present value. And the reverse operation, where we assess for how much money will be today worth in the future, is called capitalization. We won't be dealing with capitalization at all. I just mentioned it here just for completeness sake. Now, this is the main, or the very simple formula for describing the present value. This is basically a division between the future value and a discount rate, and the n, which is the number
of years.
Sorry?
Number of years.
Yeah, I can see that. I'm just looking mentally at what the term is mathematically. It's a number of years between present and the future. Now, the higher the discount rate in this division here, the lower the present value of the future cash flows. You can take a simple example. If you have what is the present value of 1,000 euros in 7 years? If the discount rate is 10%. Don't ask me yet what the discount rate is. I'll explain it in the next slide. So simply a division. So the present value theory says that 1,000 euros today, 1,000 euros in 7 years is worth today 513 euros. And if the discount rate is 15%, that will be even less, 376. So as you can see, it's all dependent on this number. Obviously, the number of years as well, but it all has to do with what choice of discount rate that we make. Now, the discount rate essentially refers to the interest rate used in the discount cash flow to determine the present value of future cash flows. It takes into account not just the time value of money, but also the risk and the uncertainty of future cash flows. So the greater the risk and the uncertainty, the higher the discount rate. An example, if you're doing something, a business which is very risky, you're selling weapons, for example, you may have lots of potential future cash flows, but you cannot really bank on them because you don't know if you find enough customers, because for whatever reasons. This risk is incorporated in the discount rate, and usually it's higher. So this is a high risk endeavor that you're doing. In the energy business, if you do something which is very mature and very secure, if you're building a natural gas power plant and you have a long-term contract with a supplier, then the discount rate for what you're going to be doing is going to be low. If you're investing something which is of lower maturity or high uncertainty, then the discount rate might be higher. This is something that is quite relevant to the building of specific plants, mainly nuclear plants. So what about inflation? Some of these calculations take inflation into account, and some of them don't. The nominal discount rate doesn't, and the real does. So the real discount rate is the productivity of money, as it's called, is the nominal discount rate minus the inflation rate. So be aware of that. So when you, sometimes the analysis that you see referring to a real discount rate or a nominal one of them takes the account of the inflation rate, the other one doesn't. So what is the NPV, the net present value, which was a question yesterday? So it is the difference between the present value of cash inflows and the cash outflows of an investment project. So it estimates the amount of wealth that the project creates over a certain period of time, and you nominally you accept the project if the NPV is larger than 0. If you have mutually exclusive projects, you accept the one with higher positive NPV, which means it has a higher investment value. So NPV is basically a single metric that gives you a monetary value, and the way that you look at it is that if it's higher than 0, then you tend to think that this is an investment you want to do. If it's less than 0, this is something that you don't. Here's a simple example. It refers to the future cash flows discounted at present value minus initial investment. So D is the discount rate, N is the number of years, and CF here is the total cash flow. Now, if you look at the analysis down here, you have the cash flow for year 0. Usually all investment projects, in anything, not just energy, have a year 0 when the initial costs appear. In practice, that is not always true. Projects take more than 0 time to construct. So this is a bit more complicated, but for completeness sake and for simplicity's sake, we're going to be assuming that everything happens at year 0. So it is the initial cash flow, which typically cash outflow taking a negative value, and you have the cash flows for every year. For year 1, year 2, year 3, and then you divide, you add all these terms, and you have a discount rate here, which we discussed already, which is in the power of 1, power of 2, and power of n, or how many years you want to do the analysis for. It's usually 20 or 25 years. That's a typical time span we do for energy projects. Here's an example. I'm using dollars here instead of euros. It's the same thing. So a project requires initial investment of $100,000. Over the next 5 years, it's expected to generate the following cash flow. All positive. That's year 1, year 2, year 3, year 4, year 5. Okay. Why is it like that? It depends on many reasons. You may have taken a loan, there's taxation, there's operation maintenance schedule where in one of the years you have to change something in the equipment. It doesn't matter. All the cash flows are positive. So if we take the assumption that the discount rate is 17%, is it a worthy project investment? So the NPV formula, we substitute the 100,000 euros, which is the initial investment here, as a negative value because this is something that we pay. And then we add all the positive cash flows for the rest of the years. So if we do this simple, arithmetic calculation, we end up with a number which is 18,378. So what does this say? Should we do the investment or not? We should, because it's more than zero. If we had a mutually exclusive project that had an NPV of 40,000, then we would choose that one, because that it's a higher NPV. Of course, assuming that everything else is the same. Now, the NPV is it takes into account the time value of money, as we said, because it calculates the present value. It considers the cash flow stream in its project life. It represents the value being added to the investors, because this is important. We're talking about the investor's point of view now. And it's fairly simple to calculate. It doesn't need much data. But it is dependent on the discount rate used. And this is a contentious issue. We'll talk about it a bit later and on what the brackets are acceptable of using. And some people find it difficult to work with a monetary return rather than a percentage return. Some people are thinking of the rate of return that you get from an investment and not so much of a monetary value. But it looks simple to compute, and it is. But you have to know that it's one of the main indicators when you're trying to assess an energy project. NPV is one of the main ones. Now, let's move on. Any questions before we move on to IRR?
I have just a problem with the definition of the present value.
Yeah.
If you can please just, it's the future value divided by 1 plus discount rate.
Let me go to the.
I think it was this third.
Sorry. Present value. Here it is. The next slide. Okay, yeah.
Because normally the future value is always less than the.
Well, the future value in nominal terms. So it's that's why the example is like that. So it's 1,000 euros in 7 years. Okay, that's why you have this 1,000 year here. Well, basically this is a reduction of the equation to the present day. So if you have something which is 1,000 euros in 7 years, how much is it worth today, and not the other way around? It isn't trying to assess of how much worth is 1,000 euros today in the future. It's the opposite calculation. But the main point to remember here is that basically that the amount of money that you have today is worth more than the same amount than what it will have in the future, because, as we said, money has this interest earning potential. This is a theoretical, classical economics concept, of course. In practical terms, it depends really on the context. In certain economies, this may hold true. In other economies, without actually going through a depression, that may not be so true. But this is a point that we can discuss if you want later in more detail. Now, where were we? Okay, here. Now, let's go on to the next indicator, the IRR. This is the rate of return that makes the NPV, as we said, of all cash flows, both positive and negative, from a particular investment equal to 0. So we are actually looking at what is the discount rate that makes this calculation that we actually showed before for NPV to become 0, which is actually exactly the break-even point. So it can be defined as the discount rate at which the present value of all future cash flow is equal to the initial investment, or the rate at which an investment breaks even. This is actually now a percentage term and not a monetary one. Now, the IRR calculation, should I go back if you want to take a look at this equation again? Am I moving too fast or too slow? Fine. Now, the IRR calculations are commonly used to evaluate the desirability of investment projects. So assuming that alternative projects require the same initial investment, the project with the highest IRR would be accepted. So the higher the project's IRR is, the more desirable it is. Now, a project is accepted if the IRR exceeds the discount rate used to calculate the NPV, and this is crucial. In other words, if it exceeds the cost of capital. I think this is better illustrated in an example, which you will see. So let's take again the same sort of numbers. A project requires initial investment of $100,000. Over the next 5 years, expect to generate the following cash. Again, positive cash flows, year 1, year 2, year 3, year 4, year 5, the same numbers as before. And assuming a discount rate of 17%, is it a worthy project investment based on IRR? We'll do again the NPV calculations as we did before, but now instead of actually having this set at 17% as we did before, we say that this is the number we're looking for, and we equate the whole thing to 0. Okay. And and if we try to make some sort of parametric analysis and put various values into that IRR term here, we get this curve. So well, this point here is where the NPV becomes 0. So the discount rate there is, sorry, how much? It's exactly between 24 and 28%. So as you can see, the computed NPVs, when you have a discount rate of 0, are all positive, and then at this point, the sign changes, and everything here is negative. This is shown with the curve here. So by doing that, we compute the IRR where the NPV becomes 0, which works out to be this number, 27.68. So for the initial assumption that we did, that the NPV calculation was made with a discount rate of 17%, this number is higher. So in that case, we should say we should accept this project. And IRR, practically, an IRR of 27% is extremely high. You probably wouldn't see something like that in the real world. An IRR of 10 or 11% is really good. Depending, of course, again, on which economy we're talking about. There is a complication with calculating IRR, because there is a chance that so any investment project can have only one NPV, but under certain cases may have more than one IRR. And this happens when there's a changes in the sign, where the cash flows become basically become negative at some point. So, example, considering a project with an initial investment of 235,000, you have a 540,000 inflow in year 1 and a 310,000 outflow at the end of year 2. So what's the IRR? So you have here the initial money that you pay for the capital investment, then you have a positive one, and then you have a negative one. What happens to the IRR? What happens to that curve that I showed you earlier, this one, if you have such points? Well, it will become like that. It will be like this. So you have 2 points where the IRR makes the NPV equate to 0. One of them is at 10%, one of them is 20%. So what do you do in this case? What's the IRR of the project? Well,
to look at the discount rate and then to see which one the higher.
Yes, but as you can see, if the discount rate falls into this area or into this one, then the NPV is negative. So if the risk-appropriate discount rate is between these values, these two values, then it falls under this small part of the curve, then we should accept the project. Otherwise, reject. That is what the theory tells us to do. So sometimes this is called MIRR, for multiple IRR. It's not used that frequently, but the occurrence of changes in the sign of the cash flows is fairly common. So you should take care of which IRR you use, because you might get an erroneous value. So for the IRR, it takes into account the time value of money. Again, it considers the cash flow stream in its entirety. It makes sense to people who prefer to think in terms of rate of return and find absolute quantity like NPV somewhat difficult to work with. But it's relatively more difficult to calculate than NPV. And its multiple IRR is useful, but it's rarely employed. People just prefer one single number. So is that clear, what NPV and IRR are? Yes? Okay. Now, let's move on. Let's go on to the one metric that you probably most heard of, the simple payback period. This refers to the number of years for the cumulative net cash flows of the project to equal the initial investment. So you have here the investment costs, and then you have the net annual cash flows. By doing this, basically, what you get is a time period. So we have a 60 million initial investment, as an example, a 20 million annual cash flow, and a 1.5 million annual maintenance. So this is what's called the net annual cash flow. So you take the annual cash flow here, and you subtract the maintenance. So you say that for the payback period, you will have 3 years and 3 months for you to get the money back, let's say. So the shorter the payback period, obviously, the more desirable the project. 3 years and 3 months is again extremely small. Energy projects, classical energy projects that use fossil fuels, used to have a payback period between around 15 years. Renewable energy projects, and depending on what sort of support you're giving them, have a payback time for about 10 years. But if we're talking about larger ones, they could be larger. But lately, with all these auctions and all the improvements that we have seen, actually this number could be less. There's a variation of the payback time, which is called the discount payback period. It doesn't, instead of using instead of using simple cash flows as it is here, the net annual cash flows, as we call it, it uses discount cash flows, which we explained in the first few slides what a discount cash flow is. It's the same as the one used for calculating the NPV of a project. Again, the decision criteria is that the shorter the discount payback period, the more desirable the project is. And in either payback period, a project would be accepted if its payback period is less than a pre-specified number of years. If, for example, the shareholders of a company decide that we're going to be investing in this project, if the payback period is less than 10 years, then you just do this calculation, if it's less or if it's more. But it's one of the indicators in your arsenal. You should never rely on just one thing. Doing all these calculations is important. Hello, Professor Blanco. Welcome back. Again, strengths and weaknesses. The advantage is that it's a measure of risk and liquidity. It's very useful for evaluating small projects, but it ignores the time value of money, at least the simple version of it. It ignores, very crucially, ignores the cash flows after the payback period, because when we have reached that point of saying that we have amortized the project and we have all our money back, what happens after this? It doesn't take into account that. It only calculates the fact when up to the point that you reach the payback period is complete. It is an objective metric in how many years, and is not consistent with investment theory. Again, as I said, it's one of the things that you should be using, but not the only one. You should consider all the other indicators, the ones we have talked about in the beginning. Now, all investment criteria, have their advantages and disadvantages. In practice, when making an investment decision in project analysis, we should use several criteria, as I said. NPV and IRR are the most commonly one used, primary investment. Payback is commonly used as a secondary investment criterion. All right, all clear? And let's move now to the metric which is more relevant to the energy and electricity world. Now, the levelized cost of electricity is often cited as the convenient summary measure of the overall competitiveness of different generating technologies, and it represents the per kilowatt hour, which means per unit of energy, in real terms, of building and operating the generating plant over an assumed financial lifetime or duty cycle. It is the most usual metric cited when trying to compare electricity and sometimes energy in general of generation plants. The beauty, let's say, of it is that it's a metric that we can use across all technologies. So we're using the LCOE to compare renewables, to compare fossil fuels, to compare whatever, and then you find a single number that you can compare it with other technologies. It doesn't say the full story, and we'll explain that in a bit, but it's a very useful starting point. So, what does the LCOE calculation include before we go into how it's calculated? It has installation costs for sure, financing costs, taxes, not always, we have to be careful, the operation and maintenance, salvage value, any incentives, also the quantity of electricity the system generates over its life, if we're talking about an electricity plant, and the degradation and decline of output. There's an asterisk here. When we're talking about cogeneration plants, we were discussing yesterday, it's a little bit more complicated to calculate the LCOE because you don't have the same commodity. You either have to compute two different ones, one for electricity and one for water, whatever that is, or find a way to combine them together by making some assumptions. It doesn't always include the environmental costs or the transmission costs or other hidden costs that a project may have. So looking at this number, you have also to know a bit about the assumptions behind its calculation. Now, by definition, the LCOE is the project costs that include all, as already said, installation, operation, maintenance, and all that. And over the quantity of electrical energy, usually in kilowatt hours, generated by the system in that year. This, of course, if you just transform this equation, can be written like that. So the project costs are the LCOE times the quantity of electrical energy. Is that clear? Now, the accumulation of project cost over the project's lifetime gives a total life cycle cost, which is, again, this one. We use a discount rate here. Is used to calculate the present value. We discussed about that in the first few slides. So if we substitute the value of Cn here that we had in this previous slide, we get this. So this is the total life cycle cost. Okay? It's just simple substitutions of values in these equations. So if you combine those calculations, you have this one here before, which is equals to that. And if we solve for LCOE, we get this final equation, where you have the discounted costs in the numerator, and you have the discounted electricity or energy production here. This raises an interesting question, because what exactly is this? What does it represent? What is a discounted energy? You can discount the value of money, but how can you discount the energy? Any ideas? Well, actually, it isn't a real thing. It's a convention that we use to make this calculation. You can't really discount energy, but for convenience sake, or for the sake of the specific calculation of the specific metric, we take this kind of approach. Because we cannot really have discounted cash flows of money, but absolute values of energy in the future. So again, there's a difference between the real and the nominal LCO, as we discussed earlier. And the real values account for inflation, and therefore have sometimes a different discount rate. The nominal values appear usually to be higher, and there's a reflection, of course, at the time of occurrence, so they do not include the inflation rate in them. The tax hedges are applied on nominal revenues, and the relationship between those two is governed by this simple equation, where this is the discount, the nominal rate, and this is the real rate, and this I is the rate of inflation. We should be careful when looking at LCO figures, because some of them are cited as real values, or some of them are cited as nominal values. So we should know which ones, if they include the inflation rate or not into their calculation. So let's see now an example that relates to what we have been discussing for the whole week for CSP. The LCO, as we said, is a monetary value, which is basically no, it's not monetary. It's an indicator that has a monetary value on its numerator, and it has energy in its denominator. So this is the range we're discussing, and it's for this example, which is basically a chart taken from SAM. It has the lowest solar multiple for the lower LCOE for solar multiple for about 2.5. So you know what solar multiple is? Okay, we will have a slide later where I describe in better terms what it is. So this means that the solar field will supply 2.5 times the gross nameplate capacity power block. And the storage, if you add storage to this graph, you could alter the graph by moving the axis, the curves along the horizontal axis. This is the real one, this one here, and this is the nominal one. Okay, this one takes account of the inflation rate, the other one does not. Yes, this is the lowest point. Now, for technologies such as solar and wind that have no fuel cost, relatively small variable O&M cost, the LCOE changes in rough proportion to the capex of generation. Capex is the capital expenditure, as well as incentives to target the capex, such as tax breaks or grants, etc. Now, when you have technology with significant fuel costs, which includes all forms of traditional generation, all fossil fuels, these costs significantly affect the LCOE. However, it's a single-dimensional number, and it fails to capture a number of things. First of all, the true value of system with storage. It is when you add storage to a system, the LCOE changes according to, well, you'll see examples of how it is later. The dispatchability of the plant, how is it to respond to changes in the demand, and other services such as voltage and frequency support, and all these have a monetary value. You may have a lower LCOE for a PV generating plant, but which does not offer any of these. Which is lower than what a CSP plan would be. In which case, you need to know all these things as well before you're making an informed decision. An example of LCOE is the grid parity. This is where an energy source can generate electricity at a levelized cost that is less than or equal to the price of purchasing power from the electricity grid. It has been for a long time the holy grail for planets and academics. It has been reached in many countries for when we use renewable energy sources. But we have to be careful when we're talking about from the point of view of the retail consumer or the utility. These are different costs. The utility obviously has costs for generation. The retail consumer has also other added costs, taxation, profits for the company, and all that. So this is, let's say, this line here represents the grid parity. This is an example. This is actually taken from a Fraunhofer study in 2013. And this is a projection that they made for CSP. So they thought that the band of plants that would reach the grid parity would be somewhere there between 2020 and 2015. And for PV, it would be like that. So that, of course, depends on which DNI and which country we're talking about. These things would be shifted up or down if you're doing that in North Africa or in Sweden. But this is also something that, reaching the grid parity is an important metric.
Just referring to your slide, when you say LCO is classical price purchasing power from the electricity grid, you mean the retail price or the...
Yeah, that's why I differentiated here. It depends on if you look at it from a retail consumer or from a utility perspective. Normally, the LCOE should not. It shouldn't have the taxation and all the extra cost that the retail consumers are facing.
What about the profit?
No, these things should not be calculated.
Wholesale price?
In a way, yes, but then again, I said if you go back to this slide, it's all these assumptions that we're making of what we put inside and what you don't when you.
Yes, because we then define the financing cost.
Yeah, we'll talk about the financing cost now and how it affects the level of LCOE. So again, I'm not going to go into details, but you've seen that a lot over these days. These are the four models that we have in terms of. Yeah, okay, you know about this already, I hope anyway. Now, before we go into looking at what happens with the LCOE in CSP plants, we should talk a bit about the capacity factor. I mentioned it yesterday. Do you know what it is? Do you know what the capacity factor is? For those that don't, it's the ratio of the actual output in energy units to the theoretical output if operating at full nameplate capacity. So you have a baseload generation that can be in the region of 90%. Which means basically that the plant is operating at nameplate capacity all the time. For hydro plants, typically around 50%. For intermittent renewables, it ranges between 15 and 50%, depending on location, on technology, the presence of storage, obviously. And for CSP with no storage, it's typically around 20-30%, but this can go significantly higher if you include storage. And for some plants, these things, if you add storage, can reach these levels, can have a capacity factor close to baseload generation. Rely on that for most of the time. Now, again, the solar multiple determines the receiver's nominal thermal power. It's the ratio of the receiver thermal power to the cycle thermal power. So if you have a solar multiple of 1, means that the aperture area, the total area of concentrators and mirrors in a CSP facility, is required to deliver sufficient thermal energy to the power cycle to drive its nameplate capacity under desired conditions. You decide what the design conditions are. And you will very rarely find a CSP facility that has a solar multiple of 1. Facilities with storage usually have higher than that, 2.5. So the solar multiple with system and storage should be close or equal to 1. Of course, it can never be actual, or it can be equal to 1, but to account for all the losses, you should probably have that slightly higher. System with storage has higher solar multiples depending on the size of storage and techno-economic optimization study. Now, for the costs of CSP and ST plants, the upfront costs, usually you have a solar field, the receiver, the storage, the power block, and others, as we discussed yesterday, the salination, solar cooling, and all that. You have the land and site preparation costs and EPC costs. These are the main categories. There are also some other things that you can include here, but this is like a top-down overview. Then you have the OPEX, the operation maintenance costs, and finally you have the financing and taxation costs. Let's see now the upfront costs for a system has a 6-hour storage. It employs a solar multiple of 2 and has a DNI data for Cyprus. That's why I have been showing you all these slides about the solar multiple and the storage, because I want you to understand what's going on in this chart now. So let's go to the first one. We have 4 categories here of troughs, tower, linear Fresnel systems, and dish. Just a word here that these are costs that I indicate where they are. It doesn't mean that it's always like that in every case. And the data is taken from SAM, from in 2017, the latest edition. SAM is the program that you worked with Cyril the other day. So as you can see, the site improvements for all systems are roughly the same. Again, remember, this is for a 100 megawatt plant. I didn't put that anywhere. No, I didn't, and I should. Oh, it's here, yes. It's 100 megawatts electric nameplate capacity plant, so which means it's a big, it's a large plant. This is a solar field cost. As you can see, this is the biggest cost, at least compared to the site improvements, and it takes the towers and the LFR system and the dish system a bit higher than what the troughs are. That's with, again, with 2017 assumptions and based on some default data that we use to show these charts in a, let's say, in a unified manner. This is the tower, receiver, and category of the tower, receiver, and heat transfer fluid system. Again, the tower system here appears to be the most expensive, and then we have the LFR system, the troughs, and the dish. You will be wondering why we're using towers so much. It's so expensive, but this will become apparent in a bit. This is the storage. For 6-hour storage, there's a relatively higher cost for troughs. The reason is of the low temperature, and a relatively higher for LFR, and then the smallest one for tower. I didn't put anything here because dish with storage is something that doesn't really exist. It exists only experimentally, but it's not deployed commercially. So as you can see, this is where these systems have an advantage. Moving on, this is the site improvements that the overall. Sorry, this is the power plant. This is what you have in the end to produce power, the power block, the generator, turbines, generators, whatever you want to use. The dish systems, as you can see, have a smaller percentage of that because they use Stirling engines mostly, and these are cheaper overall compared to these. But let's say that this is, and we have to add in the end the balance of plant, which takes the cost of the towers a little bit higher. For such a system, a little bit over 470 million, this is in dollars, roughly the same price for troughs, a bit lower for LFR, and considerably lower for dish. So why wouldn't we choose this one over all these? Why isn't that commercially successful?
It disguised the fact that storage is not included.
Yeah, that's right, that's correct. Which actually impacts a lot the capacity factor, which is shown here. That's the capacity factor plotted on this axis on the right-hand side. And the capacity factor for the tower systems compared to its cost is higher compared to the troughs and the LFR and the dish. This doesn't obviously tell the whole commercial story. Troughs have a large track record behind them and they're very mature. But as you can see with towers, and especially because we can reach higher temperatures, the potential for a system which has a lower LCOE for each generating unit is higher than the other technologies. Yeah.
When we do this kind of comparison, like do we suppose that both of them they use the same HTF? For example, the tower I think uses
yeah, no, it's not. It uses the most default dominant technology, which is oils for trough and different for tower. So it's not exactly a like-for-like comparison. It's like-for-like in terms of the nameplate data, the storage, the solar multiple, the DNI, and the size of the plant. But then, because it's so many variables, I cannot really show everything every permutation. But this is, let's say, taking the
balance of plant is everything that is not included in, like for example, is the monitoring system.
Yes, exactly. Yeah, everything that's supportive to the plant itself. Now, a word about operation and maintenance. Should I go back? Any questions to the previous slide? No. Now, these are dependent on capacity usually, and there's very little on energy production. So there's negligible variable and virtually no fuel costs, assuming that you don't have any backup, of course, generation. The operation maintenance schedule for the power block is borrowed from the power generation industry because this is a mature system we are relying on. There is cost of maintenance of reflectors, which is mainly cleaning, replacement of mirrors. Sometimes you can do breakage. The need for clean water makes deployment of such systems challenging in arid environments because you need to have water close by to clean them. The innovations of such efficient plant monitoring, low soiling furnaces, nowcasting tools to monitor the weather and be able to have knowledge of the weather conditions in a very short time period. And better understanding of degradation can reduce such costs in the future. Indication, generally for large plants, the operation maintenance costs are hard to know, mainly because they are not published, because they are owned by the plant operators. The estimations, because we are, and again, we discuss those things without, you shouldn't be taking those things at face value. It depends, of course, on the application. The estimations are that for troughs, they're around $70 per kilowatt per year, and for towers around 65. The systems, however, in more developed countries and more developed economies, let's say, have higher staff costs. So a system installed somewhere in Africa probably would have lower maintenance costs in terms of staff compared to a system in Europe, but may have costs associated with other things elsewhere. So the reductions are realized through automation of processes, washing, better plant design, lamination of mirrors. There's active research in all these areas going on. So this is a reference from Turkey, I don't know how to pronounce this guy's name, in 2010. It's a bit old now, but it gives an indication of the operation maintenance cost for 100 megawatt plants. So the variable costs, as it was said, are very, very low, but for all these fixed costs, you have solar field and storage, which account for 30%. You have insurance, which is 24%, which is important. Staff costs, which, as we said, are going to be lower or higher, depending on which economy it's deployed on, and the power block. So this is mainly where you actually spend the money on operating and maintaining a CSP plant. And these are the ballpark figures that you should have in mind when doing your calculations. Now, a word for the weighted average cost of capital. This is to determine, and actually we're going to be seeing a few slides that use this indicator. That's why actually I showed the slide here. It reflects to the cost of financing, and it can be a significant outlay and should not be ignored. It actually shows the credit worthiness of an investor. And many of the engineering companies that do installations in energy, not just in CSP, have a WACC associated with them, which basically shows how much credit worthiness they have in the market and how cheaply or expensively they can borrow money from credit institutions. It takes into account stock bonds and long-term debt. I don't know if you want to go into details about this. I actually have a slide, but let's not do it now. It doesn't really matter. For a firm, it's calculated like that. There's the value of equity, the cost of equity, the value of debt, there's the cost of debt, and the corporate tax rate. So you take all these things into account before calculating the WACC, which is the average the cost of debt and equity financing. Do I have this slide or do I not? No, I don't. So equity financing is, equity is basically when you have a stake in a company, and debt is debt financing when you actually ask money from a credit institution outside. A combination of those two is used to calculate this weighted average cost of capital. Now, again, here's another thought bubble, is the ways of supporting any renewable energy system. The feed-in tariff, which has been very prevalent in Europe and across the world for a number of years, is now on its way out. It's basically a guarantee, a specific monetary rate for every kilowatt hour direct to the system. It's usually supplied by a governmental utility. Yoros knows very well about it. He works for the Stat Department in Cyprus and has been dealing with these things for many years. And he can actually tell us a few more things if he has time at the end about what's going on with support of renewable energy installations. What's going on now is that we're moving towards bilateral agreements between a producer and a utility. These agreements are called power purchase agreements, or PPAs, similar to the feed-in tariff for the producer, but the money is not being supplied by any centralized authority. It's being supplied by an agreement between the seller and the producer. There are other measures that include supports for upfront costs, like tax breaks. This used to be very, very popular in the United States. But all the other more complex schemes exist, like net metering and conditional tariffs, depending on time of delivery. It also depends, of course, when you have an electricity liberalized market where the amount of energy that you inject into the system depends on what time it is and if it needs it or not, and what sort of quality this energy is. So these may have different monetary values. Governments may give support for these kind of things when they want, for example, electricity at the peak times of the day, either during the noon hours or the early evening hours. So let's do a test case for a 4 megawatt electric ENFNL system. An overview of the technology, you know that. You've seen the presentations of Alaric, and I think you visited the system yesterday? So, okay, you've seen it firsthand, how it looks like. Let's have an analysis of the system costs. Let's assume that it's 12.8 million or 3.36 euros per kilowatt hour. That's the overall cost assumed. That's a debt fraction of 7% for 15 years. That is the rate at which, what's the name? What's the word now? The interest rate, yes, thank you. The income tax rate is at 12.5%, which actually reflects what the income tax rate, what the corporate tax rate is in Cyprus. And this is the depreciation schedule. It's linear 10%. I think this is how it is in Cyprus, isn't it? It's linear 10% for projects like that. So this you have the system cost, a breakdown of system cost. Most of it comes from the solar field. It's about 44%. This is a power plant. There's 4% of contingency, EPC costs, land, and all that. So you can have a breakdown. Oh, sorry. This is when you actually get the system and run it through a simulation for the energy to power block. And basically, this comes from SAMS, again, is one of the charts that you can output. This indicates the total power incident. This is the thermal energy to the power block. You can see all these losses in the winter, and it performs much better in the summer. This is the gross cycle output. You can see again the efficiency losses from the power block to the cycle. And this is actually the amount of energy that is dumped, which is not used, produced but cannot be absorbed. Sorry, yes, I think probably missing a slide here. I apologize. There was a slide with the results, but oh, it's here, sorry. Now, another thought bubble for depreciation. It represents the decrease in value of project assets over the analysis period, mostly due to wear and tear. It's actually not real cost, but it's an accounting principle to reflect the fact that equipment bought or built loses value over time. Depreciation affects everything that we own. Your car depreciates its value, your house, everything. It loses value over time, and this is actually, depreciation is a monetary representation of this fact. Many countries demand specific schedules to be used. In Cyprus, the law dictates that about a 10% straight line, and the depreciation schedule is used for all renewable energy projects. In other countries, for example in the US, it's common to use non-linear schedules, which basically have a kind of something that looks like an exponential curve. 10% linear schedule means that after year 10, which is after one reaches 100% of its depreciation value, the assets will be considered to have been depreciated, actually, which means that having no resale value at all. 10 years is a relatively short time. So, this is a plot of the discounted cash flow of a specific, well, maybe let's assume that this is for the LFR system that I showed earlier, where you have this initial outlay of money, which is the capital expenditure in year 0, as you can see here, and then you have those positive inflows of positive cash flows, as we showed in the first few slides when we were discussing about the NPV. Now, as you can see, here the depreciation schedule ends, so the calculation for depreciation here is no more. So you have here the end of financing, so that's why you don't have to pay the loan back anymore. That's in the year 15. That's where you get all this jump up into your income. And then this little bump here is the addition of salvage value. That depends whether actually your equipment has any value after 25 years of operation. And from that, you can calculate those indicators we have been discussing all day. This is an IRR of 10%, an NPV of 2.23 million. This is a PPA that is reached, let's say, assume that we have a PPA with a utility for 24.8 cents, which makes this investment worthwhile. The plant's capacity factor is 22.06. So is the required PPA of feed-in tariff realistic nowadays for such a thing? If you want to have an investment like that has a positive NPV value and an IRR of 10% and looks like this, then you would require a PPA of 24.8. Is it realistic? It depends. Probably not. What you see lately for large plants are values which are much lower than this. They approach values which are less than $10 per kilowatt hour. And you can do a parametric simulation. You can allow the PPA to vary between 12 and 30. And then you can actually assess how the net present value and the internal rate of return change. As you can see, as we showed before, this is where the NPV becomes 0, which is around a PPA value of 0.21. For everything lower than this, it is negative. For everything above this, it's positive. And again, the IRR, which is the brown bars here, the increase, which is actually shown on this axis here. For this PPA price, which is about 14, the IRR is negative, is less than 0%, let's say, which indicates a really bad investment. And it goes up to about 10% here, which is higher, much higher, at about 28. There's many possibilities of optimization of these numbers, but the takeaway point here is that if you see an investment like that in renewable energy, you probably shouldn't go ahead with it, because for having positive indicators of NPV and IRR, you would need a PPA price which is in the mid-20s, and that's probably unrealistic. So what's going on generally in the world? We have here plotted the US dollars per kilowatt hour, or let's say the LCOE for all these different technologies. This is taken from an IRENA report in 2016, last year. So you have biomass, geothermal, and hydro. These are the size of the bubbles shows the size of the system, and all these are basically cases that show how much they cost and in which band they belong to between 2010 and 2016. So geothermal seems to be cheap. Hydro has a lot of cheap presence here, but of course the potential for hydro generation is very limited. The solar PV has shown a distinctively downward trend in terms of cost between 2010 and 2016. You can see all these things here being installed with a cost between even below 10 cents up to about 30. This is solar thermal, much fewer data in the IRENA database, which also shows a downward trend. And then you have offshore wind and onshore wind. Appears that the solar thermal systems are expensive, and at least historically they used to be, but lately things have started to change. So how do we expect the LCOE to fall or to progress, to move for CSP and ST plants? For parabolic troughs, temperature increases are expected to drive a reduction in costs, which is, with the switch over to salts as a high heat transfer fluid will also contribute. These are what the contributing factors to a reduction from the 2015 LCOE to what we expect in 2025. This is from another report by IRENA and DLR published in 2016. So the prices here that we see in 2015, we expect those to be about 37% less in 2025, and these are the reasons we think that this is going to happen, or at least they think this is going to happen. Most of it comes to temperature increases, the solar field direct costs, the storage, and the owner's cost, also some EPC. If you take the same thing for troughs, the reduction is higher. From about the same starting point in 2015, sorry, we reach in 2015 something which is less than 10 cents. In this case, it's slightly higher in 2025. And most of it comes from operation maintenance, which basically comes mostly from experience. The heliostat field, which has to do with different materials, different algorithms of placing the mirrors, but mainly the indirect EPC cost and the owner's cost. These are costs associated with the companies that have actually taken up and installing new projects. And if they can themselves reduce the cost so much, then overall the projects are becoming much, much more viable and much more competitive compared to traditional generation. I mentioned earlier the effect of the weighted average cost of capital, which reflects the cost of financing, which is again an indicator of a specific installer of how much credit worthiness they have on installing systems. This is taken from the same report. We could have an impact on LCOE which is tremendous. It goes from 0.8 to about a little less than 20 cents by changing just the weighted average cost of capital for the installer. That's for parabolic troughs for 2015 and 2025, and that's the same thing for solar towers, 2015 and 2025. The fact that we actually have now large corporations that are mature enough to be able to command a WACC which is relatively low means that the financing costs come down and they can push the system costs down without actually having so dramatic improvements in technology. Just by, let's say, loading these systems onto a vehicle which can now actually do these things with low financing costs. These are historical CSP cost data. This is the investment costs for projects installed in 2010 up to 2016, and this is the capacity factor. As you can see, some of them have a relatively high capacity factor, some of them do not. These usually are without storage between 2010 and 2016. And this is the LCOE, which shows a downward trend from about 31 cents going down to 22 or 24, which is still relatively higher than what the traditional generation has been. But lately, that was about a month ago, Aqua Power in Dubai announced this PPA, which is actually down here, even much, much lower than what the trend you would have expected. And there's also been some auctions in Chile and South Africa, I can't remember where, which shows agreements in this range, very low, which is actually now in the same ballpark as traditional generation. And closing, because I think that I should stop because we have the final part of the presentation done by Professor Blanco. We should talk about the value, between the value and cost. First of all, about maturity. Wind and PV have a much larger installed base and have enjoyed large-scale deployment and break the cost down. In the operation value, the CSP with storage avoids generation cost of baseload generation and provides ancillary service to the grid. It can also help avoid the cost of building new conventional generation by having these characteristics, and enables increased penetration of other forms of intermittent renewables. So those technologies don't really work against each other, but they can work for each other. If you have more CSP that can act as baseload generation, it allows for more intermittent renewables to enter the system. This is just a few targets that have been around for quite a long time. This is the Sunshine Initiative that plans to have a generation cost of about 6 cents per kilowatt hour until 2020. And they are well on their way. There's another initiative in Austria, the Australia Solar Thermal Research Initiative, where I think Professor Blanco has been actually the head of. And the EU also has a target of 10 cents, but this is not a unified strategy towards that goal. This is a small graphic that shows the 2020 goal from the Sunshine Initiative. So, thanks very much. This is the first part. We were talking about let's say, the classical deterministic approach. Professor Blanco and I will discuss about work that is being done on the stochastic side.
Can I ask a question?
Yes, of course.
Is there any specific calculation for the value of salvage value? How can we?
I don't know. Manuel, do you know an answer to this question? If we can have
in real life, in real projects, when you do feasibility studies, most of the time they consider no value. They don't
zero. Yes,
it's
good as it.
But of course it has. But in most cases, when you do the calculation, you put a value to be in the conservative side.
Actually, may actually have a cost of decommissioning, not even a value.
Yeah.